Hi guys, I'm Hedgeberg, starting this video for the umpteenth time. I keep screwing something or other up and don't get into my groove correctly. Hopefully this time will be the one that sticks. Anyway, it has been 4 months since I recorded the last video. I let that slip away from me. I want to keep doing these. I promise I'm going to try to do more. Anyway, it's time for lecture 2 of my analog design video lectures. I hope that some people find this exciting or enjoyed the last one at least. Exciting? Really? I don't know if I would ever call analog design I would call it exciting. I enjoy it. Anyway, today we're going to be talking about op amps. And we'll cover what that is in a second. What you need to know is stuff from the last lecture before you can tackle this. Namely, we talked about resistors, voltage, current. I should really add an undo button on my stylus. Voltage, current, and Ohm's law, which relates voltage to current. Also, I wanted to take a quick moment to point out that I am using a tablet and GIMP instead of my iPad, which I was using previously. So it's going to be a little bit weird getting used to my handwriting on this. I know it's not great. I am borrowing my partner's tablet. It's a little weird. Anyway, so what we're going to cover in this lecture is circuits beyond resistors. Because we talked a lot about resistors last time, but frankly, without anything else to do, a circuit that's just resistors is really kind of boring. So it's important for us to talk about what we can actually do with these circuits moving forward. So op amps are a great place to start with that, and we'll talk about that in just a moment. So I'm also going to go ahead and talk about where this will go from here, where the course will go, and that should be enough for us to get started. This is going to be pretty singular in terms of topic, so it might be a shorter lecture than the last one, but let's go ahead and get to it. So, new, okay. So, what is an op amp? An op amp stands for Operational Amplifier. So stands for Operational Amplifier. In a circuit schematic, it looks kind of like this. It's a triangle with a minus and a plus on it and some lines sticking out of it. What does that mean? So an op amp is going to be, for many of you, the first time that you've ever seen a circuit element like this, because we talked about resistors, but a resistor is what we call a passive element. This is an active element, meaning that unlike a resistor, which has 2 nodes, the reality that this one also has, this one, in addition to having 3 nodes instead of 2, this one actually has what are called power rails. So there's a voltage that is being supplied. Yes, plus and minus. There's a voltage which is being supplied, which allows this to operate. And without this, it won't operate. That means that there is actually latent power dissipation in addition to the power being dissipated by the signal coming in. It also means something else. It means that it can add power into the circuit and that it's not necessarily draining power from the circuit. Fundamentally, it is draining power from the supply rails because you can't defy the creation of energy. That's not the right way to phrase that. You can neither create nor destroy energy, but you can't dissipate it. And any circuit is going to be dissipating power to some extent. It's just a question of how and where. And so when I say that, I mean that there's no power being dissipated in the signal path, unlike with a resistor, which is going to be dissipating power. But all of this is getting way, way more in depth than I needed to about something very simple. What the hell, man? Okay, I'm sorry about that. Let's keep moving. So what does an op amp do specifically? So this can be described with a model. And so this is going to be the first time that we actually see what is called a dependent voltage source. So if you have your minus input and your plus input, the way that we describe an op amp or model an op amp inside is like this. So we say that there's an impedance between these nodes, which is R sub I, and then we have this. Don't worry, I'll get to what that is in just a moment. So here's V out. We're going to name this Vx, and we're going to name this RO. So we'll say V minus here and V plus here just to make it a little bit clearer. So the way an op amp works is that it sets Vx equal to A times V plus minus V minus. In this case, A is a factor of the op amp. It stands for amplitude, but we usually use it to refer to voltage gain, meaning it is the ratio of these two signals subtracted from each other to the strength of the output. Only in this case, it's not the output, it's Vx, because the output is separated by a resistor. But this is a first order model, and this is a more realistic model of an op amp than what you'll see usually for most of what you guys are doing, because you get to make a little bit of a simplification for the majority of things, which is that you get to deal with an ideal op amp. So wait, let me go ahead and copy this lasso tool. Oh, there we go. Control C, new layer. Let's go ahead and Control V. That's not in this layer. Control Z. Let's go ahead and... Can I paste in layer? I actually have no idea. Edit. Paste into. Nope. Right click. I can't merge down. I guess I gotta Control click. Shift click? No. I do not know how to... Whatever. We're just going to redraw this. I'm not going to mess with that. I'm so bad with selection stuff. I don't know what I'm doing. There we go. So, let's go ahead and redraw the previous diagram. Nope. Do not do that. Man, I am a disaster. Okay, there we go. There's a little tiny dot selected, which is making it impossible for me to draw on this layer. If anybody has any tips on how to do better at GIMP, please tell me. So let's go ahead and come back here to V minus, V plus, RI, plus minus, V out, Vx, R out. So we call Ri, or R sub I is equal to our input impedance R sub O is equal to our output impedance and I'm sorry for the complications earlier. I'm still going to be awful at Git. We have A, which is equal to voltage gain. And we're going to call Vx our source voltage. Now we'll call that our internal voltage. That's a better way to name that. these terms may not line up with what your professor or your books use, and that's a pretty standard thing when it comes to engineering. So we're going to say Vx equals A times V plus minus V minus. So what does all of this mean? Input impedance is the impedance that we encounter if a current or a signal is moving inwards, and it experiences some kind of impedance along the path as it moves from V minus to V plus. So that's the input impedance. The output impedance is the impedance that the signal moving out of the op-amp experiences. Voltage gain, as we discussed, is a fundamental property in terms of amplification, and Vx is our internal voltage, as we just discussed as well. Now, we're going to talk about specifically ideal op-amps. So from here on, you can forget almost all of this. Why? Because we get to make some assumptions in the case of an ideal op-amp. The first assumption, RO is equal to 0. What that means is that Vout is equal to Vx, meaning we don't even need to worry about this anymore. 2, Ri is equal to infinity. This means that there is no current I from minus to plus equals 0. And the last one here is going to sound very wonky. 3, A is equal to infinity. Therefore, seems a little weird, right? There's a really good reason for it. So the reality is that A is never actually infinity because it's simply not possible. But it can be very large, on the order of 100,000 to 1,000,000, depending on the op-amp. And for the case of simple circuit design, like you guys are going to be doing in this lecture, we don't really need to worry about gain, and we'll talk about why right now. Basically, when you design with an op-amp, you use these simplifications to make life a lot easier. The hardest one to understand, though, is the infinite gain. What that actually implies is that in the case of negative, and no, none of this makes sense right now. I know. I promise it will make sense in a second. Negative feedback, V plus equals V minus. And again, this probably sounds really counterintuitive considering that, as we talked about earlier, Ri is equal to infinity. So how does this happen? How would these become equal if they're not even remotely connected? It's a really, really neat thing. And this is where we start talking about feedback. An op-amp, as we talked about a moment ago, has two ports, a minus terminal and a plus terminal. When we said earlier that Vx, which we'll now go ahead and change, so we can scribble that out and say Vout, since we know that RO can be assumed to be 0, Vout is equal to A times V plus minus V minus. If V plus and V minus were anything other than 0, because of the fact that gain is infinite, the output would be infinite. So this equation actually really becomes useless. But it does tell us something. For any case where V plus isn't equal to V minus, the solution to this circuit is trivial. It's infinite. And that's not possible. You can't have infinite voltage. You can't have infinite current. It's not possible to create that kind of energy. And circuits are just a way of moving energy from one place to another effectively. So, if that's the case, from here we can actually throw out this. But there's something interesting. Remember this equation. I'm not going to actually cross it out. It's being dramatic, but I want you to remember that. I'm going to do something here. I'm going to go ahead and take this, and I'm going to connect it right here. I'm actually going to go ahead and erase that last line. And then I'm going to take this, and I'm going to go ahead and provide us a signal. So I'm going to call this VI. Here's the thing about VI. VI is there is no current from VI into the circuit because of the fact that the impedance from here to here is infinite, as we talked about. So let me go ahead and delete that so nobody gets too confused. So the current in is equal to 0. What does this get us? I do actually know. I want you guys to think about that for a moment. The answer is pretty simple. V plus is equal to V in. Now here's the thing. When you have this loop feeding back, hint hint, from the output into the negative terminal, that means that V minus is equal to V out. So let's assume for a moment that V plus is equal to V minus. What happens if V minus goes in any direction? So, for example, let's say that V minus increases in value. Well then, V plus minus V minus goes to a negative value. So if V minus is larger than V plus, this value is negative. And that means that V out in our equation goes to negative infinity. But wait, if V out goes to negative infinity, then now V minus is less than V plus, meaning that V plus minus V minus goes to positive, giving you V out going to positive infinity. And wouldn't that mean that this is going to oscillate? It's going to just jump back and forth between two really large numbers? And you can't see it, but I did a big hand wave here like I would actually do if I were teaching a lecture. And the saving grace is that the assumption that the gain is infinity is not actually true. You can't get infinity, like I said, so the reality is that this value is non-infinite. And the result is that these two forces fighting to control V out will actually drag V out to a point where the minus terminal and the plus terminal are the same value, because anything else will cause V out to go in the opposite direction of the change, bringing V minus back into stability. And this is negative feedback. The idea that you can use an op amp and take V out and supply it back to V minus to create a stabilized circuit where V plus is equal to V minus. The opposite is positive feedback, which you're basically never going to do. Positive feedback is a problem because if you think about this, where we just talked about, going from one value will cause going in one direction will cause V out to go in the other direction. It's exactly the opposite with positive feedback. V plus will go in the same direction as V out, meaning that all of a sudden your op amp will just go straight to one of your rails. And then that might cause too much current to happen inside of it, and it'll get dragged down to the other end, and you will actually get oscillation. Positive feedback is a thing that can happen. And so it's something to keep in mind when you design. You never want positive feedback, basically. If you're a more advanced circuit designer, there are cases where positive feedback could actually be useful. But for anything you guys are starting with, you don't want to touch positive feedback. But we now have this idea of negative feedback. All of a sudden, an op amp this black box circuit, which we unfortunately I can't really describe how it works internally, but this circuit creates a really, really fascinating value to circuit designers for a couple of reasons. Let's go ahead and go to a new layer. So the first thing being that you can go ahead and come back to this circuit that we had previously. Minus, plus. Oh, and I should summarize. The result of all of that we were talking about is that if we talk about our third assumption, assumption 3, assump 3 implies that since A is approaching infinity, oop, that's a bad infinity. Since A is approaching infinity, therefore, V plus is equal to V minus when there is negative feedback. So let's actually come back here to our, which layer was it? Was this our one? Yeah. So this is what this is going to imply now. Let's go ahead and keep this in mind. Nope, that's the wrong thing. Also, I'm sorry for all of the toolboxes being on screen. I tried to do this the right way, and it didn't work. And so I tried to have the toolboxes off screen while I was doing this, and GIMP decided that it did not want to play nice with OBS, and it made things a little bit trickier than it should have been. So I just went ahead and started doing a monitor capture. So let's go ahead and say that we have, as a result of A being equal to infinity, V plus is equal to V minus in negative feedback. What does that mean for circuit design? Let's go back to that last slide. Specifically, it means that we can use the nature of an op-amp to improve... Why? Oh, because there we go. I was working in the wrong layer. We can use the nature of an op-amp to actually do some circuit design tricks. For example, let's say that we have a very, very weak input signal, Vin over here, something which could not handle if there was a very small resistance that led to a lot of current. We would deal with what's called signal degradation. But we can buffer that signal because of the fact that V minus equals V plus here, and because they're tied together, V out is equal to V minus, so V out equals V plus, but an op-amp can provide its own current. It has zero input or zero output impedance, meaning it can supply as much current as it wants. In reality, that's not totally true, but that means that if I had a really, really small ohm, really small load, you know, something like 1 ohm, an op-amp could be used to drive that. Examples of small ohmage loads occur all the time in the wild. One example is a speaker. It's really hard to drive a speaker because they have a very, very small impedance. So we use circuits like this to make it possible to drive them. We add a buffer to go ahead and protect the signal from degrading as it's delivered to the load. So you'll never see a circuit this simple for driving a speaker usually. There's some other stuff that goes on, but that's the idea. So this is what we call an op-amp buffer. And it shields the voltage supply. Now it shields the, I should say, the signal source. From a small load. Shields the signal source from the load. And that's basically it. That's what a buffer is. You can also think of the term buffer is used in chemistry, if you've taken chemistry, in that a buffer is something that helps to insulate at a certain pH. So there's a lot more, though, that this op-amp circuit can be used for. When I actually took my first design course, the professor told us that the op-amp was the single most important integrated circuit in history because of what it enabled for the telecommunications industry. And there's a couple of examples of what that specifically is. One of which is this little guy right here. So let's go ahead and do a minus and a plus. Also, by the way, I hope you guys like the crickets in the background. I am recording with the window open because it's absolutely beautiful outside, and I don't know, I think that the crickets are soothing, and hopefully it'll help some of you learn a little bit better. Anyway, there's V out. So let's go ahead and say that V in is right here. We're going to take V plus and we're going to ground it. What we want is V out in terms of V in. So how do we even start? Because this is kind of weird. So this is where the assumptions that we started talking about earlier come in. The first thing that we're going to do, first thing I should actually do, is name these. So R1 and R2. So the first thing that we have to remember is that V plus is equal to V minus because of one of our assumptions, namely the infinite gain assumption. That means that V minus is equal to ground. So V minus equals 0 volts. Okay, sure. What does that give us? Well, that gives us a couple of things, because now we actually know the direction current is moving. Let's assume that V out is a positive value. So we've got current going this way. Now, that means that current's going to come down along this leg, and it'll hit this branch. We would say that some current comes in here, but it definitely doesn't because of our second assumption that there's infinite input impedance. That means that all of the current is going to move along this direction. That means that all current goes from V out to V in this case. So let's go ahead and say that the current, we'll call this I.O., moving along this path, has to be, therefore, going back to Ohm's law, V out minus V minus over R2. And since V minus is 0, this is equal to V out over R2. Cool. So moving right along, now that we know the current, that same current, because of Kirchhoff's current law, is going to also move this way. That means that V minus... Wait. That means that... So because V equals IR, sorry guys, spacing out a little bit here, V minus V in is equal to IO times R1. But V minus is 0, so we have negative V in is equal to IO times R1. IO, we've solved for. Negative V in is equal to V out over R2 times R1. Now, then we said we wanted V out in terms of V in. We can get that right now. V out is equal to negative R2 over R1 times V in. And that's it. So think about this circuit in a simpler method, in a simpler way. let's say that R2 is 10 and R1 is 1. So if we say that R2 is 10 ohms and R1 is 1 ohm, that means that negative R2 over R1 is equal to negative 10. So, negative? Seems a little weird, right? Let's go ahead and assign a signal to our input. Vin is equal to sine of x. So if you know sine of x, let's go ahead and do our basic trig. Sine of x looks like, wait, am I thinking of cosine or sine? I'm thinking of sine, right? Yeah. So it's going to go back and forth, like so. So that means that V out is equal to negative 10 sine of x. So we're going to go very far, not to scale here. So what we've done is we've taken our signal and we've flipped it and then stretched it way out. We've made it much, much stronger. So the voltage of this signal has increased, or it has gained, about 10x. So in this case, we refer to the gain of this circuit, which is the ratio of the voltage out to the voltage in, as, well, divide V out by V in this situation, negative R2. Oh, sorry. Come on. Negative R2 over R1. We call this circuit an inverting amplifier. And that's one of the most fundamental circuits that you'll actually see in just about any analog circuits project. Amplifiers are incredibly important for anything, the basic example being audio. A lot of you have listened to music. Music is a sum of sine waves. It's just a lot of different frequencies. A really quiet song is not something you can hear. You can't listen and enjoy music in its fullest if it sounds like this, if it's just really, really quiet. So the value in this case is that we can increase the magnitude of these songs by driving a larger... We can increase the magnitude of any signal by driving it or by inserting one of these. And this allows us to create a much, much larger signal. And this is really important for a lot of circuits, because there are going to be a lot of circuits where you're dealing with small voltages or low power signals that you can't necessarily drive. So let's go ahead and move on to the last circuit that we're going to cover, which is the last example of these basic op-amp circuits. And these basic op-amp circuits look like... The last of these basic op-amp circuits is the non-inverting op-amp. Or not op-amp, non-inverting amplifier. Three guesses as to what that does. Going once, going twice. Yeah, it's the same thing as an inverting amplifier, but it doesn't invert. And the way that we make that is a little different. So let's go ahead and do minus, plus, and the way this is going to look is like such. So here's Vn. Here's V out. let's go ahead and start off by looking at the circuit and thinking about what the different things are. We're going to be doing this in a nodal method. What that means is that we're going to be picking nodes and using that. So let's go ahead and define one node here, which is V minus. If we go ahead and say that current is coming out from VO in the same way that we did in our last circuit, and coming down this way, then this should be immediately obvious as to what it's referring to. Or this should be immediately obvious as to what the behavior of these two resistors are if you watched the last video. This is a voltage divider. So that means that we can save ourselves some time and say that V minus is equal to R1 over R2 plus R1. Okay. So, knowing that, if we know that if V minus is R1 over R2 plus R1, we also know that V minus is equal to V plus. Therefore, V plus times V out. I'm an idiot. So that means that V plus is equal to R2, sorry guys, R1 over R2 plus R1 times V out. But we don't want V plus, we want V in and V out. Good news is V plus is V in, so V in is equal to R1 over R2 plus R1. Let's go ahead and figure out the gain of this, because we want V out in terms of V in, or we want the gain. Well, that's as simple as dividing both sides. So we can divide both sides here. So times 1 over V in times 1 over R1 over R2 plus R1. And that means that V out over V in is equal to R2 plus R1 over R1, which is equal to R2 over R1 plus 1. So, basically the same thing as the previous circuit, only have this added factor of 1. So the gain for this circuit can actually never be less than 1. So you can never use this to attenuate a signal, but you can use it to boost a signal and not invert. And there are cases where that matters. There's not a lot of cases where that matters, but in some cases it does. So this is your non-inverting amplifier. And that's the basics of op amps. And if you know this, then you actually know how to build circuits to create gain. And that's pretty fundamental. This might actually be one of the most fundamental steps in circuit design. Yeah, I kind of don't know where to take this after this. I guess we should talk about where the course is going to go from here, actually. Yeah, let's go ahead and take a moment to go ahead and wrap up, though, the lecture first. So, what did we learn? One, what is an op amp? Two, what are the op amp ideal? What are the ideal op amp assumptions? 3, how do I choose the gain of an op amp circuit? So these are your questions. And I want you guys to go ahead and make sure that you can go back and answer all of these. If you can answer these, and you can design, let's say, I've got one. It's pretty simple. Let's go ahead and make a quick non-inverting amplifier here. Go ahead and give you guys a simple problem. R1, R2, V in, V out. What I want is if R1 equals 10 ohms, assign a value for R2 such that V out over V in equals 10. And so you can go back and you can derive this. I could actually make things a little bit trickier. I don't think I'm going to. At some point I want to go ahead and make a more complex set of problems for this lecture, and I might actually do a video on walking people through those. But I'm not totally sure when or how I would go about that, so that's something I still need to think about. Anyway, yeah, that's all for this lecture, but I want to take a few moments to actually go ahead and talk to people about what goes on here, and what the next steps are going to be. So first of all, I want to go ahead and talk about the fact that I'm going to be, let's go ahead and do housekeeping. First off, I'm going to actually go ahead and start a Discord for this course right after this. I'm going to go ahead and put the link in chat, or in chat. Sorry, I'm too used to Twitch streaming. Link in description. The other thing is so for those, there might be a lot of you who are learning this without knowing that I actually do Twitch streams. If this is something that you're interested in, I'd actually really recommend that you come and join us in the Twitch streams, which will also have a link to my Twitch channel in the description. And the last thing is that I am actually, as of right now, before I put this video up, planning to go ahead and start a Patreon. There's a couple of reasons for this, because of the fact, mostly, I want to be able to make more of these videos, and I really like making these videos, but the issue is that they take a lot of time. In just the failed recordings for this single video, I think I actually botched it enough to have like 45 minutes of footage before I actually managed to get my groove on. I think I stopped recording and restarted like 4 or 5 times. And that'll get better as I record more of these. But that's a lot of time to commit to a project like this. And as much as I wish that I could without having any qualms, I do unfortunately need to also somehow incentivize that. And that means that I am going to be starting a Patreon in order to try and give me some kind of financial motivation to make more of these without having to worry about my time. Money is expensive. And so that's something that if you guys enjoy these videos, or if you think you know somebody who does, the Patreon link is going to be in the description. And I would really appreciate it if you considered adding to that, becoming a Patreon subscriber. I am never going to paywall anybody from seeing these videos. All of these videos will always be available for free on YouTube. So I don't really know how I'm going to do Patreon rewards. I have some ideas, including sending people failed boards from my streams and failed experiments, so people can just have these weird-looking disaster boards that I've created, things like that. The other thing is that if I can reach over a certain threshold, I can make more of these videos, so it'll probably start at something like once a month, and then twice a month, and then weekly, and then maybe multiple times weekly, depending on how much the subscriber level is. So if that's something that people are interested in, I would really, really appreciate the donations. I think that this is something that I really enjoy doing, and I think that this is something that a lot of people can benefit from. And so if this is something that you appreciate, consider donating to the Patreon. And if you enjoy learning this stuff, please consider come joining us on the Twitch streams. I stream usually every Tuesday, Thursday, and Sunday, but right now I have major deadlines for my job. There's a conference coming up called Chi, and I have a ton of work to do to get ready for that. Abstracts are due tomorrow at noon, and the final paper is due not long after that, and I have a lot of work to do for that. So the streams may be a little bit irregular because of that during this time period, but you can figure out what those streams are, when those streams are planned, by following me on Twitter. And I will post any stream announcements, whether canceling or otherwise there. So that is everything. I think that's going to be it. So let's go ahead and also talk about the next lecture and what the course is going to go on to from here. So there's a lot of things that I want to cover, and I'm still working out the order. But the next lecture, I think, will be L and C, inductor and capacitor, passives. So we just talked about an active component, and we're going to go back to passive components. For these are going to involve differential equations, but we can skip those mostly. And once we're done with that, we can then start going into, from there, we can go into stuff like filter design, and then once we have filter design figured out, we can go into much more complicated circuits, stuff like Butterworth filters, we can go into stuff like RFID. That's actually a really fun thing to talk about. Audio amplifiers, all kinds of stuff. So there's a lot of places for this to go, and I still need to figure out a structure to ensure that people are learning stuff while discussing this, and advancing their understanding of the concepts. But what am I talking about? Well, so this covers us for most of this, but then we can go into the next level, which is transistor level design. And transistor level design, I can't believe I forgot about it, is one of my all-time favorite things. It's what I do professionally. So all of these things are very, very valuable skills to the modern electrical engineer. Even though the world is quickly going digital, these things still have a very important place. And so if you are interested in these things, stick around. I think with that, I'm going to go ahead and wrap up. So I'm going to say, if you guys enjoyed this, tell a friend. Let me know in the comments. Let me know if there's anything I can do better. I'm going to go ahead and post the Discord link. And if you guys want to come and talk to me, by all means, please come and shout at me. I will be there, and I will try to answer every question I can. In addition, there is also the Reswitch Discord, where I do switch hacking work, and you can come and ask questions there. And I think that's it. So, questions, comments, concerns, feel free to leave a comment, or come to the Discord and talk to me. Until then, I'm going to go ahead and I'm going to get that Patreon done. And by the time I upload this, all of that will be set to go. So I think that's everything. Thanks so much, guys. I'm going to get going. I'll see you next lecture. Until next time, I'm Hedgeberg.